All right, so we've seen the direct policy search way, where you essentially the object of interest is this policy, a strategy that will take histories and choose an action, or a summary of the history and choose an action. A summary of a history, there's another word we could use to describe it, to refer to it, and that word is state. So from now on, I'm going to think of policies as mappings that will take some states and produce some actions. And I'm going to make this even more general. So the states could be histories, but they could be something else. So if I have some latent variable, if I have an understanding, if I have a representation about the world, so if I have neurons that are firing with some rate and so on, that's the state. The state is essentially whatever information I have stored in my memories, etc., that determine which action I'm going to choose. And in particular, the policy now may not only be stochastic, but it could also be deterministic. So in the previous class, I restricted myself to the class of stochastic policies. And that's somewhat simplified the analysis. It's also possible to do the policy gradients with deterministic policies, but we won't have time to cover that in this course. If you're interested in that, I suggest you Google deterministic policy gradients. There's a very nice paper about that recently. There's also ways of casting direct policy search as inference. So for those of you who might have done a machine learning course where you learn about the EM algorithm, expectation maximization, formation models and so on, I think some of you might have seen that before. It's possible to phrase that optimization problem as an inference problem and use standard techniques of inference to solve it. It is also possible to cast it in a Bayesian setting and then use Markov chain Monte Carlo methods to solve that problem. So there's been really a lot of work on policy search from many perspectives. Dynamic programming is the other area that, there's been like thousands and hundreds of thousands probably papers on this topic. And instead of using expected returns, we're now going to introduce a slightly different quantity, which we're going to call the value function. And as the name implies, the value function essentially tells you what's the value of being in a particular state. So S naught is essentially being in a particular state at time zero, at the initial decision period. If I'm about to make, if I'm going to be in an environment where I'm going to be choosing actions according to some policy, what is the value that I start here versus starting, I don't know, maybe in London or so. And so essentially, if I had the value of every possible state, this right now is an infinite dimensional quantity. This is the function. The value function now is a function that takes as input any state, all the possible states of the world. There could be an infinite number of possible states. This could be a huge thing. So in particular, if x is just Rn, then obviously there's an infinite amount of possible states. So S could be discrete, could be continuous. I'm going to first derive the dynamic programming algorithm without making any assumptions. Of course, it's not going to be obvious how to compute this because this is not a function over infinite dimensional spaces. But then we will make a simplification, and the simplification will be that we will replace these functions by neural networks. So we will approximate them. And that's what's going to lead to neuro-dynamic programming. Neuro-dynamic programming is essentially dynamic programming where we replace these functions with neural networks. So again, neural networks are function approximation tools, so a good function approximation tool, so they'd be good function approximations of the expected returns. In a sense, we're sort of predicting the future here, but instead of trying to predict each quantity one by one, what we're doing is we're going to predict the sum of the things that will happen in the future. And in particular, of these, the things that we will care about are these quantities that we call returns. We will learn to predict the future rewards. Because if you can predict the future rewards, then you can act better. Now, we don't know which, the setup is we don't know what the future states will be. So we need to make the best decision. We need to compute the value of something regardless of what the future states are. So again, we have the sum over all possible future states. And in this case, I'm actually making it even harder because this sum could go to infinity. So now we will be really in trouble if we try to unroll the sum. Since the sum is going to infinity, so if you're summing rewards till infinity, you might think of, oh, okay, that's going to blow up. And so we're going to prevent that, and we're going to introduce this quantity called a discount factor and raise it to the power t. The reason why we're raising to the power t is so that future rewards will matter less than most immediate rewards. So depending on the choice of gamma, you'll be paying attention to different horizon. So in a way, we're sort of cheating here to deal with the credit assignment problem. Another way to think of this, if you're more sort of probabilistically inclined, is we're essentially placing a geometric distribution when we believe we're going to get a reward. So 1 minus gamma times gamma t, indicating that you get rewarded at time step t. But it's the most intuitive way to think about it is just a discounting of future rewards. To make things easy, I'm going to make the reward depend on the transition. So when I'm in state st and I act according to the policy, so I take so this is basically at, so I choose action at, I move to state st plus 1. Okay, so I'm in a sort of dynamic environment, I'm in a particular state, I take an action and I move to the next state. And of course here the expectation is over all the future states, so the distribution is over S1, S2 and so on. S naught is given, so it's an input. So I take an S naught and I evaluate its value. Take another S naught and I evaluate its value. Okay. This is the key equation. Everything we're going to do next will be techniques for solving this equation. And you can see how hard it's going to be to solve it. Once again, we have this expectation that's intractable. We have sums going to infinity. This right now looks like a very hard thing to compute. And so the dynamic programming will be just a strategy for computing it. But before I proceed, are there any questions about the setup? Or what questions are there? Okay, everyone happy? Who's unhappy? Good. I love honest people.
Is there an implied relation between the value and the policy?
Pardon?
The value of a state and the policy, is there any implied relation?
Yes, very good question. So there is. So the value depends on the policy. So we write this notation over and over and over again, and after 10 years you sort of forget to explain it properly. V depends on pi. Thank you for that question. That's really important. If I choose a bad policy, if I start somewhere, I start in state S naught, and I choose a bad policy, I might end up doing very poorly, even though I started in a good place. So I might start really close to the treasure, if I'm searching for a treasure. But maybe I decided not to turn around, and I just use a policy where I just walk in a straight line, never turn and explore my environment. In that case, I will do really badly. So the value depends on the policy. Now, I'm not going to go into theory here, but essentially there's a lot of beautiful theory behind this. I recommend, there's a very nice reinforcement learning book by Csaba Svepesvari that's available online. And in the appendix, he proves a few of the key theorems that we need to understand. Things like this is a contraction operator, and by that, what's meant is that this will converge to a fixed point. So if you had multiple agents, that fixed point will be the Nash equilibrium. And in particular, that there always exists a policy that will allow you to achieve the best possible value function. That's another important theorem that you need to come up with. And that policy is deterministic. You don't need a stochastic policy for decision processes. You only need a stochastic policy when you're dealing with multiple agents. The stochastic policy is essentially what in game theory we call the mixed strategy. If you're playing matching pennies or whatever, you need to rock, paper, scissors. You have to randomize between rock, paper, and scissors with probability 1/3 each. That's a bit of a spoiler for if you play it again. You know exactly what to do now. And I hope my wife is not watching this, because we always play rock, paper, scissors, and she's always frustrated that I always beat her. I just randomize 1/3. Anyway, so there's a lot of theory behind this, but what I'm going to provide is with an introduction. I'm going to derive the algorithm. And after this, if you want to learn more about it, if this interests you, then I recommend you look at Csaba's book, which does not have the introductory material to the extent to which I will go over it today. So I already mentioned this, but this is the value assuming a particular policy. And then we also can think of the value assuming the best possible policy. So if the policy was continuous, I guess I will replace the max by a sup, but this will be the best value. Or a better word, the optimal value. And so that's what I want to do. I want to compute this optimal value, and I will compute, and if I find the best possible strategy, which is what I'm after, then I will be able to compute the best possible value of each state, the optimal value. So essentially, the function is what I'm trying to compute. And this function depends on pi, and I'm going to be changing pi until I come up with a function that describes the true value of each state. And once I know the true value of each state, then it's trivial to know which state I should choose. If I know where to be to get the most money, then I will make sure that I just go there. The trick here is learning what's a good value function. And that value function depends on pi, so I need to learn the best possible pi. Okay, so what we're going to do is something called dynamic programming. And let me just summarize it for short. If you're trying to compute AB plus AC, don't compute it this way, compute it this way. Okay, so we all know this trick. And this is exactly what we're going to do. The expressions are much bigger, there's more symbols, but this is really what we're doing here. So I'm going to start with the expression for the optimal value function. And then the first thing I'm going to do is this sum goes from 0 to infinity. I'm going to take the 0 term out. And now the sum goes from 1 to infinity. Okay, so I've just extracted the first term from the sum. Then I'm going to, and I did one thing that I didn't need to do here. Let me just do, A naught, the first action is taken as pi of S naught. So in general, A is equal to pi of S, So I can either write here pi of S naught, or for short, I will write A naught. So I will just pick the optimal initial A naught. I still need to maximize over pi. And that's pretty much what I've got in the next step. So the next thing that I'm going to do is I'm going to use linearity of the expectation. And in particular, this guy here has only S1 variables. So it can't come out of the expectation for S1. But because it doesn't have S2 or S3, I can take it out of that expectation. The expectation being just an integral, and if the integral doesn't depend on what you're integrating over, you can take it out of the integral. So basically, this expectation will move inside, and that's why I have it here. Likewise, there's no pi now appearing here, so because I've made it explicit in terms of A naught, so I can move pi inside. I need to do one more thing. Is my first gamma here is gamma to the power 0, which is 1. So I need to make sure that it also starts at 1. So I'm going to divide by gamma so that I get t minus 1 here. And because I divided, I need to multiply by gamma. So I divided and multiplied by gamma in this step. And now I just realized that this is the stuff that I started with in the beginning. This is just a value function at the next time step. And this is Bellman's equation, which is one of the sort of most fundamental equations. Let me show it here without the indices. So instead of writing time t plus 1 and so on, this is going to be the current state, and this is going to be the future state. Okay, so the prime indicates future. And so that's essentially what we derived here, where here I had the index 0 and then the index 1 for the future. And you had the reward, this was the value in the future. So in other words, what this optimality principle is trying to say is, if in the future, if you did the optimal thing in the future, then by doing the optimal thing now, you'll still be optimal. So you can think of this, one way to think about it is, if you're riding a bike, imagine yourself at that point at which you're about to tip and you're going to fall. And when you're at that point where you're going to tip, you just move a little tip away from tipping. And then at the next time step, you move yet another little bit from that step that could have led to the bit where you would have tipped. And then you keep moving away until you're vertical. And that's how you learn to ride a bike. You work back from the point at which you tipped. Okay, so that's called backward chaining in game theory. If you do if you have a sequence and you do the optimal of finite time steps and you do the optimal thing at the end, you then backtrack to get the optimal value. Except the way we've done it is over infinite time steps. And in fact, the way we're going to work with this, we don't need to sort of think of having to go to the future and work back, but instead we will be planning into the future. Here I'm not making the actions depend on t, so in other words, I'm assuming that the strategy is stationary. So I'm not, in other words, that the strategy is not changing with time. And this is perhaps the most common form of Bellman equation. With this, it becomes easy to derive an algorithm. So the first reinforcement learning algorithm that people come up with is something called temporal differences. And so this is very similar. The algorithms, by the way, for reinforcement learning, they will be very similar to SGD. In SGD, we have the following thing. We had the expectation of the derivative with respect to the parameters of some cost with respect to the distribution of the data. In other words, we had something that was very similar to this, and it was the derivative of the gradient the expectation of the gradient was equal to 0. The only difference is with SGD you equate to 0, whereas here you equate to a function. But we can proceed just like we did in SGD and derive a non-line algorithm. And here's one way in which you could do it. You take this equation, and I'm going to add, this is going to be the learning rate. I'm going to multiply both sides by eta. And then I'm going to add plus v of s to both sides. So this was the same trick as how I derived the SGD from the true gradient. The true gradient involved the expectation of all the data, and then SGD would only load one data at a time. So here we're going to do the same thing. We're only going to load one state at a time. In other words, we move it in the world, we observe a new state, we update our parameters, we move in the world again, observe the state, update our parameters. So the algorithm will be very much like SGD. So from here we can see that, and I'm going to not now assume that we're at optimality, but I'm just going to write the expectation for any value function. So that's going to be v of s is going to be equal to the v of s plus this guy, that is the learning rate, times oh, hang on. No, we're going to have to do something slightly different, sorry. Let me put it, we're missing one step. I apologize for that. Let me take you back one step, because we're not going to do this for the optimal value function, but we need to do this for any possible value function. And so in particular we're going to do this for any possible value function, because I need to make explicit what the policy is. So the optimal value function is the max of the action of the value function. And so I'm going to go back to the old value function. Okay, and I'm gonna drop this mainly because I don't want to write it all the time. So, but keep in mind that we're conditioning it on the initial state. Now I'm going to do what I said we had to do, and I'm going to multiply this by the learning rate, and I'm going to add v of s to both sides, or v pi of s. Okay. And now I will write this as the new v, because this is the optimal once you converge. So what I need is a recurrence that will lead to me updating v over time until I get the best possible v. V is what I'm learning. And so v pi of s is going to be equal to v pi of s and plus eta, the expectation over s prime of r of s and a and s prime, plus the value function at the next state discounted by the discount factor, minus, because I'm moving this guy to the other side, minus v pi of s. Okay. And that's essentially our expression for the gradient update. And so iterative, well, it's not a gradient in this case. In this case, we're just finding an optimum by following some equation until we get to a fixed point. And so I'm going to make this the new value function under the current policy will be the previous value function And now what I'm going to assume is that I'm going to draw a sample of S prime from the environment, from some distribution, which could depend on many other variables. So if I have a model, it could depend on the previous state, the previous action, if I'm in a Markovian setting. But it really could be any state produced by the environment. So like, for example, in Atari, you choose an action with your joystick and you see a new screen. And that new screen could be your state, the new setup of the environment. And if we draw a sample, we can replace this expectation just with the evaluation, the Monte Carlo estimate of that expectation with one single sample. And just like in SGD, we don't need to take, or you could use a mini batch if you wish, but one sample is sufficient. Because we will repeat this over and over again, so there will be an averaging over time. Oops, no expectation. And so we're going to get R of S, A, S prime, sample plus gamma V pi of S prime, sampled, minus V pi of S. Okay. And that's basically is the update algorithm. So you're in current state S, you take action A according to your policy, and I haven't told you how to define the policy. To define I will do that in the next slide. But let's assume you have a policy, you take an action according to the policy, and you move to the next state. And then you need to recompute the value function. And the way you compute it is according to this. And the reason why you're going to be computing these value functions is because these value functions will help you choose the next action. We will construct the policy using value functions. Because again, if you know the value of every possible state of the world, you could use that to decide which states you're going to follow. So that's essentially the idea. So this algorithm is called TD0, and then because it's a stochastic, it's very easy to show that there's also, and the limit is as the number of samples goes to infinity, you converge to an optimal value function. And that's pretty much the algorithm. That's how you would implement it. It's very similar to SGD. Now, to introduce the policy, we're going to introduce something called the action value function. And that's this quantity here. So we're now introducing a function that is not just conditioned on the initial state, but it's also conditioned on the action that you've taken. Okay, so, and then of course the way to go map between one and the other is by taking the max. If you have the value of a state and an action, to get the value of the state is the value of the state action pair by maximizing over the best possible action. Now, this is Bellman's equation again. And we can now, using this expression that V of S is the max of a Q, we can replace V star with the max over A prime of Q star. This is true for any, whether this is pi or star. And so we've replaced it here, but the max over this quantity is giving V must, by this definition, also have to be Q, because the definition is that V is the max over A of Q. And so we get this other recurrence that now depends on action value functions, or as people call them, Q functions. So this is exactly as the previous recurrence, but now instead of just looking at the value of a state, we're looking at the value of a state and an action. And this gives us a more immediate way of knowing how we're going to act in the world. We're just going to act in the world by choosing the action that maximizes Q of S, A. So if we compute this function, if we had a function q that for any possible action and any possible state, it would give us the value of that, then essentially we encounter ourselves in a particular situation in the world, a state S. We would use this function q, we would optimize it over actions and find the best action, and then we would take that action, and we would keep doing that. And that's essentially, this function is capturing the expected returns into the future. That's how we defined it before we wrote the whole derivation of transforming the expected returns to a Bellman equation. And so by doing this, we will find the maximum expected reward. Now, in the interest of time, I'm not going to go over this because I've got a bunch of videos and applications that I want to show you. But if you proceed just like I did with the value function, if you drop the stars, multiply both sides by a learning rate, add q to both sides, you get something called q-learning. It's a very popular algorithm, one of the most popular algorithms. But it really is the same trivial application of the stochastic approximation ideas. Now let's get into the interesting part. So that gives us all the frame. This was all done in the 50s. This was the framework for transforming infinite sums to a recurrence, and that essentially that was Bellman's work that we can solve by using essentially stochastic approximation techniques, similar to SGD. What we haven't talked about is how we're going to represent these functions. And by and large, most of RL for a long time was only doing with little grid worlds and representing those functions with essentially discrete points. And that probably is one of the reasons why it didn't work. Many years ago, many people tried to use neural networks for this, but again, the same story is always in this course that I've mentioned over and over again. The resources weren't there in terms of computation, and so people gave up on neural networks as representations. And they moved on to use linear functions, because linear functions are more tractable. And also linear functions lend themselves nicely to the theory, because everything is convex and so on. You can exploit all sorts of fixed point tricks to come up with nice theorems, but you're not solving the real problems in the world. You're certainly not being able to build an agent that will watch Atari games and be able to win just by watching Atari games. So now we're revisiting this where we're going to parameterize the Q function with parameters. So now the Q function, think of it as a neural network that takes states and actions as inputs. So the state for a game, for example, is the screen. You look at the screen, that's S, and then you need to choose the action of the joystick. And then Q will give you the value of that action. And it's going to be a neural network. Now, because we've parameterized, we've restricted the set of possible Qs to the Qs that are implementable by a neural network. So we're no longer doing exact Bellman, but we're doing only approximate Bellman. This is also known as approximate dynamic programming. So what we're going to do is introduce a loss function that measures how far we are from Bellman. So this is the neural network Q function, and this would be the equivalent Q function that you would get if you were to apply Bellman updates. So this is just the Bellman recurrence, which folks often call a Bellman backup. So that's a Bellman backup or a target. And I'm going to just write a target here. Now, importantly, the target has parameters that are not at the same. So this is at iteration I of the algorithm, and currently what we're going to try to do is update the parameters of this Q function, but for the target, we use the previous parameters. The idea there is that what we're doing to construct a target is we're looking at the previous Q function, and then we're putting this previous Q function through Bellman equation to give us a new Q function. And what we're trying to do is approximate Bellman, that Bellman backup, by minimizing this difference between this guy here and this guy here. Or another way to think about it that folks often use is to think this as an actor and this is a critic. The policy, you act in the world by following this, by maximizing over AQ of S comma A, and then the critic, or you find some parameters for your actor to act in the world, and you then act in the world, and then the critic tells you how well you've done using those previous parameters that you chose. So it's important to get this temporal thing. If you put WI here, you're going to have trouble with your algorithm. Okay, so now all that's left, if you want to learn this neural network, we now have a loss function. The states and actions are over all the states and actions we're going to encounter in the environment. So if you're playing a game, you basically pick an initial state and initial action and sort of proceed from there. So the only thing is we need to compute, yet again, the derivative of this, and then follow the gradient. And that's the same good old stuff. The gradient of this thing will be the gradient of the quadratic term, which will give you this guy, and then you need to take the derivative of this guy using the chain rule. And then you choose actions according to this. Okay. So if you want to design a reinforcement learning algorithm with a neural network as a function approximator, essentially you will choose actions according to the policy, and then you update the parameters. So so the setup is you're in state S. You start in state S. You choose A. And one of the interesting things about Q-learning, since I'm not going into the theory, I'm not going to go into it, but I will mention it because it's very important. You choose an action. You can choose an action using a mechanism that's different than the mechanism you're going to use to choose the best action when you're done. So once you've learned the parameters, once you have an estimate of the parameters, you're going to choose actions this way. But while you're learning, you can choose actions in different ways. Because essentially you're exploring the environment. So you could choose actions to explore the environment, not only to exploit, to maximize Q. And in fact, if you have knowledge that is given to you by experts, so you have other Q learning algorithms running with you in parallel, if you have many agents in the environment, they can provide you with next actions, suggested next actions. One common strategy is the epsilon greedy strategy. The epsilon greedy strategy basically says with probability epsilon, A is a sample or the max over A prime of Q of S comma A prime. So you essentially maximize the Q function, and with probability 1 minus epsilon, A is some sample from a uniform distribution over some range. So basically uniform noise action. So if you have 3 possible actions, just pick one of those 3 at random. And that allows you to explore, because you're not only being greedy, but you want to explore. There's a whole family of techniques that allow you to be smarter about how you choose the actions. And in particular, what you should be doing is choosing actions that take you to places where you don't know much about Q, because you want to learn about Q. But let's for now use this epsilon greedy strategy. Once you have chosen A, so you have S, you have A, then the environment gives you S prime, right? So you're in a particular state in the world, you take an action, and the environment changed. Now the image is a little bit small. And then you update I'm just going to write update omega using this equation. So you do one step of gradient descent. And that's essentially that's how you would implement a Q-learning agent using a neural network. Let's look at an example. And this is DeepMind's deep Q function network, or DQN for short. So we're going to use a neural network to represent a state action value Q function. I'll show that network in the next slide. And we use RL to learn that Q function. And essentially the agent is here. And the agent observes video frames, and it chooses actions using this joystick, and then it gets a reward. And it keeps doing this, and it should learn to play the game. Now, in DeepMind's system, they do one thing that is slightly more interesting than the naive Q-learning method that I just showed, and is that instead of just only using the current experience, the current state, and the current actions, they will keep a database of previous, I guess, quadruples of states, actions, next state, reward. And so this is a database of experiences, or episodes. And the idea is they want to make this great, the gradient is very, very unstable when you learn it, as I just showed in the previous slide. But by picking several things from the database, you stabilize. So the target, instead of just having a target that's evaluated, say, at one sample, your target will be evaluated at the mini batch of samples extracted from this memory. So it's like you're keeping it, you have this working memory, just like for the neuroscientists. Like imagine this is a little hippocampus, which you're picking these experiences, these episodic memories and so on, and then you're going to act using those previous experiences. And that's essentially in reinforcement learning, we call this experience replay. Okay, let's look at the neural network first. Nothing exciting here. It's the state is basically 4 video frames, and I guess they found 4 worked well. You do convolutions, not much pulling, because the image, it's not like a real image where you need pulling to deal with invariances. The images in Atari are sort of old school, yellow, red, blocky, and so on. And you do several stages of convolutions, you do several stages of densely connected layers with rectified linear units, and then there is one output per action. You could also put the actions as inputs, but the reason why they chose it this way is because it's more computationally efficient to evaluate new policies. Because basically you put in an image, and out you get Q of each action. So probably best seen here. So the output of each network, when it takes an image as an input, will be Q of whatever that image is, X, and this action, which I guess is up arrow. So each output is one of these Q values. And then if you want to pick the best action, you just pick the action which has the highest Q value. And that's how you choose how to move this guy. And the algorithm essentially is what we just went over. You take an action according to some epsilon greedy policy. The assumption is you start in state ST. So you've taken action AT, you are in state ST. The Atari will show you what the next video frame is. That's ST plus 1. and Atari will also tell you what the next reward is. Most of the time that reward is 0. It's only when you do something interesting that reward goes up. Now you take this quadruple, or this tuple, and you store it in a memory, in a database D. And then you draw a sample of 10 or so experiences, which are these tuples, from the database. And you compute the targets, that is, these quantities, evaluated at all these experiences. So basically, by drawing these samples from the database, we're going to approximate this expectation with just a sum over all those experiences in the database. So instead of just using a single, this is basically like SGD, where instead of just using the current thing, we're going to use a mini batch. The only interesting thing here is that you don't even use. So this is kind of like going at random into your data, picking a mini batch, and using that to update, to stabilize the algorithm. And then to minimize this, they just do SGD. And that's essentially TQN. And it learns to do this. It learns to play things. It learns to do things even though there's delayed reward. And I think what Vlad's plotting here is basically the Q functions. It tends to have very similar Q functions. So importantly, it's the same neural network that is used to play it's the same architecture that's used to play the games. For each game, you need to relearn the parameters. But the network, it's not like you need to tune the network every time. So it's the same structure, the same hyperparameters. A current challenge is to come up with a single network, where you don't learn where you just use one single set of parameters that plays all the games. There's another one here. Let's see if I can get it to play. Oh yeah. So I got a slide from Vlad, and the title is Sacrificing Immediate Reward. So I think what he's trying to say here is that there's some elements in this game that you don't pay attention to, and you rather try to go for things that will give you more reward. I'm assuming it's that little white guy at the bottom. Does anyone play this game, Sequest? This is actually a very fun game, and it's a hard game. You can just Google this, and there's a bunch of emulators that you can play. This also says something about your age and my age. Anyway, Atari was the thing when I was a kid, back in the day. This is where it all started. Wozniak, this is what he did for the job. He built these games. Steve Jobs worked for Atari. This is the beginning of computer science. And in those days, well, here not so much, a bit earlier, the video was memory indeed. You would store to the video as 25 by 80, and you would treat video as a memory. And when you wrote your assembly programs, it was very much as if you wanted to plan how to move something on the screen and so on. It's kind of like the direct policy search algorithm that we saw before. Basically, to finish this, these are the games that it played, and all of these games, it beats human performance. So this is kind of interesting, because this task requires that the network be able to see and be able to understand video, not just images, because it's not in order to do well, you kind of want to see how bullets are moving and so on. So it has learned to capture features about how objects evolve in the world. And it's by knowing this that it can play the game. It end-to-end has learned to see, and it has learned to act in its particular restricted environment so as to maximize performance. So it's quite impressive. There are many games where it still doesn't do well, and these are sort of, each of these games is in a way a challenge for artificial intelligence. This is just some visualization. This was sort of to give you the sense of how important this work was. It made the front page of Nature, and it's not easy to get that spotlight. And this, from my days, there used to be a game called Pac-Man. They used that. So that's one of the closest things that we've seen to what we've always aimed for, AI agents. Agents that can learn to perceive the world, that can learn to act, and that are achieving some goals. And that also led to a lot of bad press about AI, most of it being rubbish, because it's speculative, it doesn't take into account limits of computer science. It assumes that everything will increase exponentially, which is just crazy. To basically take one model, an exponential, and you fit it to everything. That could be problematic. So be very skeptic when you read these papers about AI. At the same time, there are some concerns. This is really my last slide of the course. Out of this course, I'm hoping you'll be able to go and implement neural networks in Torch, and you'll be able to do some of these things, or at least you'll have the background that will allow you to read about it in a few weeks or months, be able to implement any of the algorithms we've discussed in the course, or new things, in fact. But you have to be aware of being responsible about what you're doing. Planning where to move something. You could do planning to decide how you're going to schedule nurses in order to improve NHS treatments. And that's a straightforward application of reinforcement learning. You could do amazing things for healthcare. But you could also be planning how to exploit people, how to make the most money out of them if your goal is to grow the profit of your company. That's very achievable even in the healthcare setup. You could be planning how to maximize how you take over another country while you're using warfare and so on. So there's lots of bad applications of AI, and there's good applications of AI. And I do think this technology is now very, very powerful. I mean, there's a reason why most of the work that I've shown here is basically being worked by folks at Microsoft or Google or Facebook. And I can tell you that the military is also very interested in those people. But right now it's much more interesting, I think, for scientists to work with the search engines than to work with the military or evil companies. The other folks in London, although there's there's a lot of people that are focusing on engineering, and I personally have a bias towards engineering and building useful products for society, and that's sort of, I've no doubt brought that bias into this course. There's many good things you could do, and sometimes the decisions will be hard. I mentioned as one example that 1.2 million people die every year in car accidents. Most of them are innocent, they're pedestrians. So it's atrocious that we allow humans to drive. They shouldn't drive. There should be automated cars. If every car was automated, we could eliminate accidents. They would have far better vision capability. They would be much better at making decisions. They could communicate with each other, and so on. Maybe there would be a few accidents, but we could reduce it to, if we can reduce it from 1.2 million to 1,000, we're ballpark big goal, we're still saving millions of people. At the same time, when you do that, all those cab drivers in London will be out of a job, and the truck drivers and so on. So, like all new technologies, I think the biggest threat of AI is it could put many people out of a job, including people like me, like teachers, because there's, in a sense, there's videos on YouTube, and you could probably train an AI agent eventually. And in fact, some people are already doing that, trying to figure out automatic tutoring systems. You sit in front of a computer, and the computer tries to figure out what it is that you understand, what it is that you don't understand through question and answering, to provide a better curriculum for you to learn, one that's adapted to the individual. Not like this, where I obviously have not adapted the curriculum to each of you, and certainly not to the thousands of people watching this on YouTube. And it's important to understand that, because it's important to understand that to choose your careers. as you go into the future. You know, obviously things that involve human relations, contact, and so on will be jobs that will be permanent. But a lot of jobs will eventually be replaced by AI. And the solution to that is not a technological solution. So it's important that you be aware of this and that you communicate this to folks. This, at the end of the day, will require engagement of everyone. If one day the robots take over and they do our work and we don't have to work, then the question is, how will I reach a higher economic value if I can't work? If work is taken away from you, how can you move up? So a lot of things become very critical. On the other hand, there are problems like this one, which are so complex that you can't understand, that hopefully by having smarter machines, the machines will help you solve these problems. And that's really my hope, is that we'll be able to build machines that can help us improve our world. And that's the course. Thank you.